Hello to everybody. Today we will study a single transistor amplifier. So we have seen one type of transistor which is called the MOSFET transistor. There is another type which is called BJT, which stands for bipolar junction transistor. So historically the transistor is the BJT, so it is the one that has been invented first, but it's a little bit more difficult to understand. And the MOSFET transistor is also very useful because it's the basis, we will see this, of the so-called CMOS technology, that stands for complementary MOS, metal oxide semiconductor technology. And this thing is the basis for the microchips when we will speak about digital circuits. And fortunately for us, it's also a little bit simpler to understand how it works. So we use this transistor. So this is the symbol of the transistor. And now we try to understand this circuit. So what do we have here? We have a resistor connected to a battery, and then this resistor will create a closed circuit like this. So the current will go like this inside the resistor, inside the transistor, here and here, like this. And we said that the flux of this current is controlled by the voltage applied to this third terminal, which is called gate. So now we have to consider a couple of things. So the first one is that there is a voltage drop across this resistor, and there also is a voltage drop across the transistor, what is called VDS, V drain source. And this voltage drop plus the voltage drop across the transistor should be equal to the voltage generated by the battery, by this battery here. And this is the Kirchhoff principle applied to this mesh. Okay. So then we know that by changing the voltage at the gate, something happens. So the channel inside the MOSFET gets bigger or narrow in a way that the current will change. So if the current will change, the voltage drop across the transistor, across the resistor will change. It's the Ohm's law applied to this resistor. Let's call it VR equals R multiply I. If R is constant and I is changing, it means that this delta V is changing. But if delta V across the resistor is changing, and this plus this must be always this because of the Kirchhoff's law, it means that also VDS is changing. So let's have a look of this graph here. This is called the characteristic curve of the transistor. It's something that comes with the datasheet from the manufacturer. So we already introduced these curves when we studied the behavior of the transistor. Now we have to add another curve, which is this one, which is called the load line. So in the electronics terminology, the thing that you want to, let's say, to drive with an amplifier is called load, and in this case it's a resistor. So we want the thing of which you want to control the current flowing in is called the load. So if we consider one hypothetical case where this VDS is 0, it means that conversely the voltage drop across this resistor is the entire voltage V, which we call VCC. VCC is the voltage of this battery. So in this condition, when VDS equals 0, it means that we are here on this chart at this point for VDS. Then the current is simply the entire voltage of the battery divided the resistance of the load. So it's this value. So this gives us this point. Vice versa, if we do something on the gate in a way that we are able to completely close the channel so no current will pass, then the voltage drop across the resistor becomes 0 because of the Ohm's law. So V equals R multiplied I. If I is 0, then the voltage drop is 0. But again, because of this mesh and the Kirchhoff law, if this voltage drop is 0, it means that this voltage drop VDS becomes equal to VCC. And so we are here. So these are the two extreme conditions. And all the other intermediate values of gate will set a value that stays on this locus, the load line. Excuse me. Okay, on the load line. So now we can do one thing. We can take advantage of this region, which is called the saturation region, where these curves are flat and parallel each other, almost, let's say. It's the job of the manufacturer of the transistor to produce such kind of device for which the curves are like this in this area. We will see why in a while. So if we consider this, we can try to set a point here which will correspond to a certain VDS. Let's call this value VDS 0. Okay, good. So we need to consider a point here. We call it VDS 0. And we choose this point in order to be, let's say, in the middle between this maximum value VDS and the minimum value corresponding to, let's say, a region where these flat curves will start to become not flat anymore. So something in between. So in parallel to this, which is called the VDS ID characteristic curve, we also have another graph which is called the VGS ID curve, which is much simpler. It's a straight line. So we proceed like this. Once we chose this VDS 0, which is also called the operative point, we go here, we meet this load line, which depends on the resistor we have as a load. Then we go here, we identify the corresponding ID, we switch into this graph, and then we understand which is the VGS, we call it VGS 0, for which this VDS 0 happens. So similarly, we can identify other points. For instance, if I consider this point and I do the same trick, I go here, and then I go here, and then I go here, I find a corresponding point on the VGS ID characteristic curve. I call VGS minimum, which corresponds to a point here I call VDX maximum. And similarly, I can choose this. I go here, I meet this line, then I identify the corresponding ID. I go back into this graph, I find the ID, I meet this characteristic line, which relates the ID to VGS. I project this here, and I get another point, which is VGS max, corresponding to this point, which is VDS minimum. So what is happening now is that if I read this graph the other way around, so applying a VGS input, let me try to zoom it. So if I apply a signal of VGS, so the voltage at the gate, spanning in this range, then what I get is a corresponding signal at the output, so VDS, spanning in this range, which is much bigger. And this is happening thanks to this channel modulation that the transistor operates, thanks to the voltage gate, to the voltage at the gate. So we have to notice a couple of things. So first, this range is bigger than this one. It means that the signal is amplified. Second, the signal is inverted, because for a minimum value of VGS, which is our input, then we have the maximum span for the output, and vice versa. So a single transistor amplifier like this one can amplify the magnitude of a signal and invert its phase. So I want to clarify one point, which is that this amplification is not creating energy from nothing, because one can think, okay, but I have a small signal, now I have a big one, how is that possible? I mean, the power of that signal, the power of the amplified signal comes from the battery. It's like in the water tap analogy, if you move the screw of the tap, you require a little energy coming from your hand. So let's say in the terminology of the transistor, a little bit of voltage and current also, but very little in the transistor, in order to control the position of this barrier here. But this little energy that you apply to this system will modulate also, I mean, it can modulate a big amount of energy in terms of water flux flowing in this path, because the source of this energy would be a sort of big water tank, very high in altitude. Imagine like hydroelectric power plant, and the power of this thing is not related to the power you need to control this. The same thing is happening in the transistor. So, okay. So now we have an output here, the input is sinusoidal, the output is also sinusoidal but inverted. Why there is this battery here? Because we need to give to the input a bias, this VGS0, in order to have this bias here, VDS0. And why we need to put that bias? Because this trick works only if we are in this region. So if we try to make a sort of three-dimensional plot, I did it here, say like this. So if we try to plot the VDS, VGS and ID characteristics in a sort of three-dimensional diagram, so all those curves will also define a region around this Q point where this portion of this surface is flat. And then if we see the projection of this plane here on the VDS ID graph, that would be a straight line like this. And if we see the same projection of this plane cutting the VGS ID plane, it would be another straight line like this. And those things has two angles which are different, and this makes a linear relation between the current and the voltage with different slope. And because of those two different slopes, you can understand that this signal here can be, I mean, the VDS can be bigger than this one. It all depends on the slope of this plane, which again is something that the manufacturer has to guarantee, otherwise the trick doesn't work. Now we will move to an application of this, which is the differential amplifier, which is a piece of what is called operational amplifier. So in order to study this, and the operational amplifier is what is needed in order to amplify signals in a good way, especially if we keep an eye, for instance, on the neurophysiology, we need to study a little circuit based on the MOSFET, which is called the current mirror, which is this thing here above. So I go to the blackboard, and now I draw this circuit. Okay, let's try. Let's do this. Then let's draw a transistor. Oops, too small. Okay. So here we have the drain, the source and the gate, and here we have a resistor. So we call this battery VCC. It's an historical term. I believe that it stands for voltage continuous current, because usually when you see this VCC symbol, it means that it's attached to a source of constant voltage, not the sinusoidal voltage, for instance. Okay, so we said that there is a current ID flowing in this circuit. I draw it like this. ID. going inside this mesh. And we said that there is a linear relation between the current ID and the voltage VGS, which is the voltage of the gate respect to the source. So if you prefer, just to be more clear, we can also put this in order to say that this node is the one for which for us the voltage is 0, so V equals 0, the ground. So all voltages are referred to this point. So the equation is that ID equals a certain constant which is called Gm, which stands for mutual conductance, VGS. So this thing is called mutual conductance. So it's a constant that depends on the transistor, the type of transistor we choose. So it comes from the datasheet. The manufacturer makes it in a way that it gives a value to this. Then, because of this connection, I connected the gate to the drain. So if I consider this voltage here, which I call VDS, from source to gate, and VGS, and if I consider this other voltage VDS, I notice that they are the same because of that connection. So I can write that VDS equals VGS. Now I have these two equations that needs to be satisfied. Then I can notice that VCC equals the voltage drop across the resistor R, which is RID, plus VDS, as we said in the single transistor amplifier, but this is RID plus VGS because of this connection. And then I can make some substitution. So in place of ID I put GM VGS. So this is R GM VGS plus VGS. I'm just copying this, and this is VGS multiplied by 1 plus R GM. Okay. And so if I follow this chain of equalities, I get that VCC equals VGS 1 plus R GM, and therefore from this I get that VGS equals VCC divided 1 plus R GM. I'm just doing some mathematical passages. So once I found this, I can put this thing into this, and then I can write the current ID in this way, just substituting. So ID is VCC multiplied GM over 1 plus R GM. So why do we need this? Because this is basically a current generator. So we start from a battery having voltage VCC, we put a resistor here, and then now we discover that with a given transistor, so for a given GM, a certain ID is flowing in this circuit. So this is a piece of a current generator, because now we can do another thing. We can do this. So we take this circuit and we add a little piece to it. So I try to do it here. So the battery, the resistor, the transistor, this connection here like this. And now I add another thing, which is another transistor of the same identical type. And here I put a load which I call Z. And I connect this like this. This is our ground point, VCC. So the circuit on the left makes a certain current ID flowing in this thing, and this corresponds to a certain VGS here. But now I connected another transistor equal to this one, which means with the same GM, and so for this transistor, the one on the right, this relation ID, let's call it ID prime, equals GM VGS still holds because it's the same type of transistor. So the VGS, this transistor is stealing the VGS from this other one. It means that this current I prime that will flow in this branch here. So let's consider that there is another voltage source here, VDD, attached to this node. So this current ID prime equals the current ID. Why? Because this VGS here, if I think of it as the VGS of this transistor, is the one that makes flowing this current ID according to a law which is exactly the same of this one. So I put an equal transistor here, it steals the same VGS from this one, and therefore this current should be the same. But the important thing is that this current is the same of this one, whatever is the load I attach here, and whatever is the voltage of a battery I attach here at this node. So this is a current generator, because I set the current here and the current is flowing in this branch with the same value I set here, but I have this freedom. So this thing is called the current mirror circuit. It's a circuit which serves in order to copy the current flowing in a branch.